Dear viewers, I welcome you all for this continued topic of instrumentation of UV spectroscopy. In this session, we shall cover the remaining part of UV instrumentation. We have been left out with the detector part and the sample cells and the UV spectrophotometer instruments. Coming to the detectors. Detectors are the devices which convert the light energy into electric signals that are displayed on readout devices. As I have mentioned, the electrical energy or the light energy what we come across, or the transmitted radiations which pass out from the sample cell, they fall on the detector, and detector is an instrument which converts this light energy to electrical energy so as we can find out the intensity of the radiation which is passing through the sample cell. The transmitted radiation falls on the detector which determines the intensity of radiation that was absorbed by the sample. So we have three different types of detectors in UV spectroscopy. The first is the barrier layer cell, the second one is the photocell, and the third and the most widely used is the photomultiplier tube. We have some ideal requirements for any detector which is chosen in the UV spectrophotometer. Ideally, it should have or it should produce some quantitative response. What we mean by quantitative response is the detectors should sense the change in the quantity of the sample, or they should sense the change of light or the intensity of the light that is because of the change in the concentration of the sample cell. So in broad terms, we call it as the detector should ideally be quantitative, showing the response in quantitative way. And any detector should have high sensitivity and low noise level. The noise level is crucial. The lower the noise level, the higher the sensitivity. So basically, any instrument is operating on 1:3 ratio. If the noise level is 1, the sensitivity is ideally set to 3. So that we can mask the noise level. Another requirement is it should possess short response time. Rather, it should not take too long to respond, but it should take a very shorter response timings. And also, the detector should provide signals or response in a quantitative way to a wide spectrum of radiations that are being made to fall upon. So when there is a range of spectrum of radiations we are employing, and that radiation spectrum is made to fall on the sample, and once after if it is made on the sample absorb these radiations, and some of the radiation is being transmitted. So the instrument should sense that ratio of the difference between the absorbed and the transmitted radiation in a very quantitative way, and that sensitivity should be to the wide spectrum of the radiations that are being received in that particular sample cell. So basically, these are the ideal requirements of any given detector which is employed in UV spectroscopy. Coming to the first one, that is the barrier layer cell. This is a barrier layer cell which I have taken it from some image source or some website. The barrier layer cell, as I have mentioned, this is a kind of detector which converts the light energy to the electrical energy. So what it consists? This barrier layer consists of a layer of selenium, which is a semiconductor that is deposited on a strong metal base of iron. So I will draw your attention to this image. Here you can see there is a metal base which is made up of iron, and over that is an demarcation. I mean to say there is a separation by an non-conducting layer, and over that there is a layer of selenium which is a semiconductor, and this selenium and this metal base are not electrically contacted. I mean to say they are not in contact electrically. Rather, there is some dielectric material which is placed between these two selenium and iron surfaces, and over this selenium is a small barrier over which a thin layer of silver or gold, which we call it as a second collector electrode, is sputtered over the surface of selenium. So this is the surface of selenium, and there is a barrier over which a translucent layer of a gold or silver is sputtered, so that that gold layer or the silver layer acts as a second collector electrode. So we have two different electrodes. One is the first gold or silver, and the second one is the bottom or the metal surface. So they form a part of the electric circuits. Coming to the working of this barrier layer cell, when the radiation falls on the selenium surface, electrons are generated. This selenium is a photosensitive material. Whenever there are radiations that are falling on this selenium layer, the electrons are produced, and these mobile electrons tend to move towards the silver surface. The electrons produced on this layer of selenium, they tend to move towards the silver surface, as there is a barrier between the selenium and the metal base. Okay, since there is a barrier here between the selenium and the metal base, the electrons won't travel to the metal base, rather they tend to travel to the silver or the gold surface. And once these electrons travel across this barrier layer and then reach the silver surface, there is a potential difference between the two electrodes. I said this is one electrode and this is the other electrode. Once the electrons are generated on the selenium surface, they travel towards the silver layer, and once the electrons are accumulated on the silver surface, there is a potential difference that is being developed between the two electrodes. Which are the two electrodes? The one is the silver surface, the other one is the iron base, thus leading to the flow of current. When the external circuit, if we connect these two electrodes to an external circuit which is having a low resistance, a photocurrent will tend to flow, which is directly proportional to the intensity and the wavelength of the light falling on this layer of selenium. As this leads to the generation of electrons and accumulation of the electrons over the silver surface, and thus there is a potential difference when we connect this whole thing to the external circuit which is having a lower resistance. With respect to the sensitivity, as sensitivity is moderate compared to the other two detectors which we'll be going to discuss, this kind of detectors are used usually in photometers. Okay, and this barrier layer cell is also called as photovoltaic cell. Why photovoltaic? Because there is the generation of electrons because of the radiation of the light which is falling on this selenium surface. That was all about the barrier layer cell. Coming to the next one, which is a photocell. This consists of the high sensitive half cylindrical metallic photocathode. You can see here, this is the diagram of photocell. Here we have high sensitive half cylindrical metallic cathode, which is half cylindric in shape, which is contained in an evacuated tube. So there is a cathode which is contained in an evacuated tube, and there is an anode which is fixed on the axis of the tube. You can see this thin wire, and it is almost on the axis of this particular tube. This acts as the anode, and this cathode will be having a photosensitive surface over which electrons or the light beam or the photon beam is falling upon. And this is a more sensitive detector when compared to the previous, that is photovoltaic cell or the barrier layer cell. Coming to the working of this photocell, the surface photocathode, as I have mentioned, is coated with a layer of elements like cesium or silver oxide or a mixture of both. Okay, so as to form a photosensitive surface, they choose cesium or silver oxide, or they mix both cesium and silver oxide, which forms a photosensitive surface on this photocathode. When a light radiation falls on this photosensitive cathode, I have shown here a photon beam falling on this photosensitive cathode. When the radiation falls on this photosensitive cathode, it starts emitting electrons which are attracted towards anode. You can see on falling, or when the photon beam falls on this photocathode, it gets excited, or the photosensitive surface will tend to emit electrons, and these electrons are attracted towards anode. Okay, and thus leading to the flow of current that generates a potential difference between these two electrodes because of the generation of the electrons on the cathode which are being pulled towards the anode, and there is a generation of a potential difference, thus the current will tend to flow. And it is more sensitive compared to the barrier layer cell, as I have mentioned, and therefore it is most widely used. Coming to the next detector and the last detector what we have in UV spectroscopy, that is photomultiplier tube. The photomultiplier tube is the most widely used detector in UV spectrophotometers. We'll come to a conclusion and we'll understand why this is most widely used detector in UV spectroscopy. As it is a combination of photodiode and an electron multiplying amplifier. This phototube is made up of the photodiode and electron multiplying amplifiers called as diodes. I'll come to those diodes right in this slide. It is based on the principle of multiplication of photoelectrons by secondary emission of electrons. Rather, it says it generates the, or it amplifies the electrons, or it magnifies the electrons, or the number of electrons it multiplies, so that the secondary emission is quite high and the sensitivity of the whole detector is quite increased. As I mentioned, these all detectors are the evacuated tubes. So is this photomultiplier tube, which is an evacuated tube containing one photocathode and around 9 to 10 electrodes known as diodes. Okay, there is only one photocathode and there are several electrodes, several other electrodes, we call them as diodes. And these diodes play a very crucial role, and the crucial role that they play is they amplify or they multiply the electrons striking each of them, and you see they are being arranged in the increasing order of potential of 75 to 100 volt higher than the previous. Okay, I will come to the next slide where I will show you each of these diodes are arranged in such a way that one diode is at the higher potential compared to the previous. For example, this diode here is at higher potential compared to the previous, which is plus 100 volt, whereas this is plus 200. This diode is having plus 300, whereas the previous is having 200. I mean to say there is an increment in the potential on each of these diodes as and when we move from one to the other. And the surface of this each diode is made up of, again, a photosensitive surface which is made up of copper beryllium alloy oxide. That is the reason why the electrons are being, there is only one electron which is striking the first diode, but you can see that one electron is multiplying into several electrons, and those several electrons again multiply into several, and thus they keep on multiplying once they hit and strike each of these diodes. After the last diode, we have something called as a collector electrode, and that is another electrode which is an anode, and it simply collects all the electrons which have been emitted by these diodes. So we have one photocathode here which is red in color, and there is one anode at the last which is simply collecting the electrons. So what it does, it generates a potential difference between these two, and since there is a potential difference between those two electrodes, the current tends to flow. And the basic difference between the previous two electrodes and this is, it is extremely sensitive to the light. Why it is extremely sensitive? Because when the light falls on this photocathode, that is being made to fall on the diode, and here the magic happens. These photodiodes will tend to multiply and magnify these electrons in so high quantity that the sensitivity increases several hundred times. So that was the best thing about this photomultiplier tube. And coming to working of this particular photomultiplier tube, let me take you to the next slide. Yeah. So I will be speaking here with respect to the working of this electrode, though I have talked about the working of diodes and the amplification of the electrons in the previous slide. But I would like to emphasize the working as a separate section so that we understand this photomultiplier tube in very much detail. So coming to the working, as I have mentioned, when the radiation falls on the metal surface, the photocathode emits the electrons. Okay, this is an photon beam which is emerging out of the sample cell, and that is striking the photocathode, and this photocathode is metal or a sensitive surface which is having electrosensitive surface where it tends to emit electrons, and those primary electrons which are being emitted by this photocathode are being attracted towards the first diode. Here this is the first diode, and I have mentioned previously these diodes have been maintained at the potential higher than the previous. So when the electron strikes this first diode, 4 electrons are emitted by this by the surface of the diode. These emitted electrons are attracted by the second diode, and where a similar type of electron emission takes place, and those electrons are again diverted to the third diode, and again there are more number of electrons they are being generated, and those electrons are again deflected or diverted to the fourth diode, and this sequence keeps on happening, and the electrons will multiply in such an extreme way so that the collector plate or the anode receives all of those electrons. As photomultiplier tube, as I have mentioned, it is the most sensitive of all the detectors. This process of electron emission is repeated over all the diodes present in the photomultiplier tube until a shower of electrons reaches the collector anode, as I have just now mentioned. The number of electrons reaching the collector is the measure of the intensity of the light falling on the detector. So the amount of electrons that are being reaching this anode signifies the intensity of the light that is reaching the photocathode. This is how the photomultiplier tube works, and the diode is a spatial component in this particular photomultiplier tube. Here I have a real image of the photomultiplier tube, which I have taken it from Wikipedia, where they show the several diodes. You can see them, the diodes which have been arranged in basically in this particular fashion, where you can see them like one facing the other at a certain angle. So this was about the photomultiplier tube, and this photomultiplier tube, as I have mentioned, is the most widely used and extremely sensitive detector, and even the results what we get out of this detector is really fast. So with that we are done with electrodes. The next section what is being left out in the instrumentation of UV is the sample cells. We also call them as cuvettes. So there is one special thing about the sample cells or the sample holders what we design and use in UV spectroscopy is the sample cells are made up of quartz or highly polished surfaces. The reason for using the quartz as the material in the sample cells is because quartz will not absorb any UV radiations, whereas the glass will absorb the UV radiation to a very significant extent. So if we make the sample cells with a glass, then the majority of the UV radiations or the incident radiations are taken up by the sample cell itself, and that is the reason we don't want the cells to be absorbing any UV radiations. So we prepare these sample cells with the quartz, and according to Beers-Lambert's law, the optical path length should be 1 by 1 centimeter with the 1 centimeter path length. That is what we have in a standard cell. Likewise, we have several other different forms of cells like cylindrical cells, the micro cells for our extremely low samples, and we can increase or decrease the path length from centimeter to mm so that suiting the needs of the study. And there are something called as flow cells, wherein which if there is a continuous monitoring to be done or continuous UV monitoring or the UV absorption monitoring of a sample is to be done, then they are taken into these flow cells. And this is one of the UV cell, how it looks like, and the one which we will be using in our practicals. With that, we are done with the components that are involved in the UV spectroscopy. Now I am taking you through the description of an UV spectrophotometer. There are two different types of UV spectrophotometers. The one is the single beam and the other one is the double beam UV spectrophotometer. First, coming to the UV single beam spectrophotometer, here I have tried to take the components as a block diagrams, and all of these individual components we have studied so far in the previous discussion. So here is the radiation source, and this particular part is the monochromator assembly together with entrance and exit slit, and we have seen the wavelength selectors, filters, prisms and gratings. They will act as a monochromators, and after that, followed by the monochromator assembly, we have a sample cell which could be a reference cell as well, and we call them as a sample compartment in general. And this sample cell is followed by the detector, and we have just now discussed all the three detectors that are available as options in UV spectroscopy. And this detector is followed by an amplifier or the readout device. So the purpose of using the slit is to use a monochromatic radiation or a sharp beam of radiation which is falling out of this radiation source, and the exit slit also serves the similar purpose so that we can choose a monochromatic beam out of the exit wavelengths out of these wavelength selectors. So I will come to the UV single beam spectrophotometer. I have tried to animate the things as much as possible. So once the radiation source is put on, what happens is the light enters through this entrance slit and it falls on the wavelength selector. The wavelength selector could be the prism or the grating, and once after it falls on this wavelength selector, the light tends to diffract. So after the diffraction process, we get the component wavelengths out of this single white light. We get a component wavelengths, and each of these component wavelengths will have individual wavelengths. And similarly, that happens with the grating, where we have discussed the grating surface is a serrated surface with a highly polished and sprinkled with aluminum powder, so that the grating phenomena happens. And once after this grating happens on this wavelength selectors, the wavelength or the radiation or a single wavelength is chosen to pass through by using an exit slit, and that single wavelength falls onto the sample or the reference cell, and after the absorption, the emitted radiation will pass through the detector. So the difference between the UV and the UV single beam and the double beam is, in the single beam instrument, there is no separate option for keeping the reference cell and the sample cell. Rather, we need to remove the sample cell and replace it with the reference cell. So that is what we call as a single beam instrument. So we can change the wavelength just by turning the wavelength selector. Now we have the different wavelength, and we can again change it to have a different wavelength. So it involves the movement of this wavelength selector so that we can choose the desired wavelength at a time. So that is all about a single beam instrument. As I mentioned, there is no option for holding the sample cell and a reference cell as a separate components. But that has been tackled out, and that has been added up in the double beam instrument. So before we go for the double beam instrument, This is a single beam UV spectrophotometer, the actual image of it. Coming to the double beam instrument or double beam UV spectrophotometer, we have again the radiation source, entrance slit, the prism grating or the wavelength selector, exit slit. We have something called as an additional component called as a beam splitter and a mirror or a collimating mirror. This was not present in the single beam. The purpose of employing this beam splitter is to split the beam which is emerging out of this exit slit. We split that beam so that it falls simultaneously on the reference cell and the sample cell, so that we can take the ratio of absorbances simultaneously from the reference and the sample cell. So we have two detectors here. Some instrument will have one detector so that the radiation reaches both the radiations from the sample and the reference cell will reach that particular detector, or we have two detectors of same make so that each of these radiations are sensed by each of these detectors. So let us try to animate this. The radiation source is on. A white light is falling on the grating. Then the grating does its job. The burn wavelength is selected by the exit slit and it reaches the beam splitter, and the beam splitter literally splits the beam into two halves so that one travels through the reference cell and the other travels through the sample cell. And once they are passing through this reference cell, they reach the detector and the amplifier picks up the reading. So this is with one wavelength. Let me change the wavelength. Now it is blue. The other wavelength, the other wavelength. So with these gratings we have an option to change the wavelength as and when or whatever wavelength I wish to have. So the UV double beam spectrophotometer has an option. I can start observing the wavelengths from 190 nanometers and I can end up till 800 nanometers. I can give a command to the instrument so that 1 nanometer will pass through this exit slit at a given point, like 201 passes, followed by 202 nanometer, followed by 203, followed by 204, so on and so forth. We can make a library of absorption patterns for each of these wavelengths in UV double beam spectrophotometer. So this is how the UV double beam spectrophotometer looks like. Here is the sample compartment. Here is some electronic panels to give commands and inputs. On this screen we have some basic status of these instruments and what are the parameters we are entering. Whatever parameters we enter, they tend to visualize here. And once we set the parameters, everything, we keep the sample cell here in front and the reference cell at the back. Since it is double beam, we have both the options to keep the sample cell as well as the reference cell. So this was a bit of instrumentation discussion we were supposed to have, and these are some of the references which I have taken in order to discuss these topics. So with this, I am concluding this instrumentation of UV spectroscopy. Thank you all for joining.